Let's try to understand the energetics of phase changes. As we heat up a solid, the kinetic energy of the solid molecules will increase. The molecules vibrate faster. The temperature increases, the kinetic energy increases. At the melting point, the kinetic energy is so high that the molecules shake out of their crystal lattice position and can slide around each other. The molecules are no longer fixed in the crystal and they're becoming liquid. Temperature is not changing, but the energy is going up. It's their potential energy that's changing, their energy of position. When all the molecules are liquefied, they start vibrating faster and faster. The temperature increases. As more heat energy is added, the vibrations start to be so violent that a few of the molecules, which are now in the liquid phase, escape as vapor. At the boiling point, all the molecules have enough energy to overcome atmospheric pressure. All the molecules move into the gaseous phase. The temperature remains constant because kinetic energy, believe it or not, actually stays the same. It's the potential energy that's changing. Bubbles form all over the liquid, and in time, all of it escapes as a vapor, as a gas. Now let's look at solids in some detail. The molecules of solids are held in a crystal lattice. It's a very ordered lattice, but the molecules do have kinetic energy. They vibrate around their positions in the lattice. As heat is added, that vibrational energy will increase. This is the first part of a solid liquid gas warming curve. Kinetic energy and temperature, since they are related, increase. Here we see the enthalpy change is equal to the negative Q, the amount of energy being pumped in, and that is m of the solid, the mass, times the specific heat capacity of the solid, C, times the change in temperature. Moving from solid to liquid, the molecules of solids vibrate so rapidly that they break the attraction that keeps them in their crystal lattice position. Now they can move past each other freely. They are in the liquid phase, still held together, but no longer in the lattice. The potential energy is changing as they move from solid to liquid. Kinetic energy and temperature stay the same. This is the second stage of a warming curve. Kinetic energy and temperature are constant. That's why this line that you see here is flat. So all you need is the molar or gram enthalpy of fusion and the mass or the number of moles of the substance to find delta H. And delta H, which is minus Q, is equal to the mass of the solid times the molar heat of fusion of the solid, or the moles of the solid, more likely, times the molar heat of fusion of the solid. As the liquids warm up, the molecules of liquid are already moving easily around each other, and that's why they flow well. They're fluids. As you add more heat, their kinetic energy and temperature will increase. They vibrate faster and faster, and some of them will actually have enough energy to escape as a vapor pressure. As you can see, the rising line means that the temperature is changing. Temperature increases as you put in more heat. Delta H is equal to negative Q, and it's the mass of the liquid times the specific heat capacity of the liquid times the change in temperature. The molecules of the liquid vibrating very rapidly begin to break free, and at the boiling point they become gas molecules all over the liquid. You see bubbles everywhere in the liquid. That's what we call a rolling boil. And what you have there is an equilibrium between gas and liquid until all of the liquid has turned into a vapor. This is the fourth stage of a warming curve, and you see the kinetic energy and temperature don't change. All that's changing is the potential energy. So all you need is the amount of the liquid and the heat of vaporization of the liquid to find delta H. You have the amount of liquid either in mass or in number of moles, and the heat of vaporization either in kilojoules per mole or kilojoules per gram. Finally, the gases warm up. All the molecules of the substance are in the vapor phase. You're in the realm of the gas laws here, and the higher the temperature, the more they obey the gas laws. As heat is added to this, the kinetic energy goes up, the speed of the molecules increase, and either the pressure or the volume of the gas will increase, obeying the gas law P1 V1 over T1 equals P2 V2 over T2. Here we see the final rising part of the curve, and the amount of heat that's involved, the Q minus Q, is equal to delta H. The change in enthalpy then, you have to have the mass of the gas, the specific heat capacity of the gas, and the change in temperature to find the heat change. Now, if you are cooling gases or liquids, the graph looks just the opposite. The heat given off as the gas, liquid, or solid cools is given by the equation that has the temperature change in it. Delta H equals minus Q is equal to the mass times the specific heat capacity times the change in temperature. At the phase change, either gas to liquid or liquid to solid, there is no change in temperature, so there is no delta T in those equations. You would use then the molar heat equation without the heat capacity. Delta H is minus Q, which is equal either to the mass times the gram heat of the phase change, or the moles times the molar heat of the phase change. So here's a practice cooling problem for you to do. Go ahead, read it, write it down, solve it, and then check the answer. Here's another practice phase change problem, and you can see the question and the answer here. Do the question and don't look at the answer until you've finished doing the question.